All right, so after discussing this general abstract setting of affine connections, let's look more specifically at a case of affine connections on Riemannian manifolds. Okay, so these are Riemannian connections. And just as a reminder, that on an arbitrary second countable Hausdorff manifold, there are an infinite number of choices of connections, right? So on an arbitrary sort of second countable Hausdorff manifold, which I should remark was included in the definition of what we consider to be a manifold. There are sort of an infinite there are infinitely many sort of affine connections. Okay, so in the case of a linear manifold, there was sort of a distinguished one, right? Okay, so that's basically the canonical connection. And the point is that if you're on a Riemannian manifold, there is also, in some sense, a distinguished choice. And that is what is oftentimes referred to as the Levi-Civita connection, or Riemannian connection. Okay. And it has two important properties. Which has to do with that it's symmetric and it's invariant with respect to the Riemannian metric, right? Or more precisely, Riemannian metric is satisfies some invariance property, which I'll describe. Okay. The other nice thing about it is that when you look at the restricted case of a linear manifold, then this notion of the Levi-Civita connection recovers the canonical connection. Okay. So in the case of linear manifolds, the Levi-Civita connection reduces to the canonical connection. Otherwise known as the classical directional derivative. All right, so so let's try to make sense of what we mean by these two properties of symmetry and invariance of the Riemannian metric now. Okay. Okay, so symmetry. So an affine connection is symmetric if its Christoffel symbols satisfy the symmetry property. That gamma ijk is equal to gamma jik. All right. So let's try to understand what this means, perhaps more abstractly. So what does this mean more abstractly? Okay. So in particular, it's like, can we make sense of this in the absence of a coordinate chart, right? Because in order to actually write down the Christoffel symbols, we needed a choice of a chart. Okay. So ideally, it's like one would like to be able to show that this notion is coordinate independent, right? Okay, because at least a priori, there's no, it's like reason to sort of automatically assume that, you know, this sort of coordinate or local based characterization of symmetry is actually sort of well defined, right? So to define symmetry, right, of an affine connection, in a coordinate free manner, right, we first have to introduce the idea of what is known as the Lie derivative of vector fields. Sorry, the Lie bracket of vector fields. Jacobi Lie bracket of vector fields. Okay. Okay, so let's say we have two vector fields. On M, okay, and then whose domain sort of includes, it's like an open set U. Okay, and then I'm going to look at some function f, okay, in fu, right, which is just a set of smooth real-valued functions. On U. Okay, all right, so I'm going to define the Lie bracket of two vector fields, and it's going to give me another vector field, sorry, another vector field. Okay, so if you recall, it's like a vector field that can be defined in terms of its action on a scale-valued function. Okay, and so that's what I'm going to do. I'm going to look at the Lie bracket of two vector fields acting on, and define it in terms of its action on a scale-valued function. Okay, And then this is just defined to be the following. So essentially, I'm constructing what looks like the commutator, right? So you should think of the vector field acting on the scalar valued function. It's like via directional derivatives, right, as being a derivation, right? What it does is that given a scalar valued function and the vector acting on it, you get a scalar valued function. So again, it's like if I have the second vector acting on the scalar valued function, I get a new scalar valued function, which I can then apply this vector field on to get another scalar valued function. And the same is true here, right? That except that I've reversed the order in which I've applied the vector fields. Okay, so all right, so this is again defining, it's like the Lie bracket of two vector fields, which is another vector field in terms of its action on the scalar value function. So, all right, so it is easy to show that this bracket is R linear. Okay, which means that it acts, okay, if you have AF plus BG, right, this is A bracket acting on F plus B, the bracket acting on G. Okay, it also satisfies a Leibniz rule. Or product rule, okay, which is that if you apply the bracket on a product of functions, okay, that this is equal to F times the bracket acting on the second function plus the bracket acting on the first function multiplied by G. Okay, all right, so what happens then? So these two properties then prove that this thing is an honest to goodness vector field in the sense that it acts as a derivation. It's like on scalar value functions. Okay, so therefore this is a derivation and therefore defines a tangent vector field. Called a Lie bracket. Sometimes called a Jacobi Lie bracket. Okay, so if you have now, it's like this notion of a Lie bracket, right? So let me just write that definition here. So if you have that now, we're ready to talk about the symmetry of an affine connection. Okay, so an affine connection nabla on M is said to be symmetric if the following is true, right? That the difference when you apply the commutator, when you apply the connection, but we switch the arguments, right, is equal to the bracket, the Jacobi-Lie bracket of the two vector fields. And this has to be true for all pairs of vector fields on the manifold map. Okay, so the claim is that this is the notion of what it means. It's like for an affine connection to be symmetric. Okay, so let's see what happens on a chart. So given a chart, right, and then of course if you recall, it's like once you have the chart, we can define a i-th coordinate vector field. Okay. Then for a symmetric connection, we have the following. All right, so I'm just going to look at its action and basis elements. Okay, so this is equal to the Jacobi-Lie bracket of these two coordinate vector fields, the bracket of the two coordinate vector fields, which is 0. Okay. So this is because EI, EJ acting on F, right, is DI, DJ acting on F minus DJ, DI acting on F, right? So this is the mixed equality, mixed partials, that is 0 for all F in sort of, smooth its real valued functions on M. So it has to be that this thing is the 0 vector. Okay. So, I'm sorry, that's minus sign here. Okay. So, all right, so this is identically 0. So that means that gamma k ijk is equal to gamma jik for every symmetric connection. And then it's easy to show that if you start with this property, that you will have the condition, you would have this condition, basically. So conversely, if you start with the property that these Christoffel symbols, it's like symmetric, that when you expand this thing in coordinates, you will get exactly the property you need. Okay. All right. Okay, so those that's one property now. It's like, and then what we're going to do next is we're going to define for you the Levi-Civita connection in terms of the Riemannian metric, and then tell you what we mean by it being the notion of metric compatible, if you will. Okay, so let me stop for that.